Welcome to Class 11 Computer Science. Today, we begin our journey with Chapter 1, Computer System. This chapter will give you a complete overview of how computing devices process data. So what exactly is a computer? It is an electronic device programmed to accept raw data as input, process that data, and generate meaningful results as output. And remember, the physical hardware and the programs running on it, known as software, together make up the complete computer system. Let's look at the hardware components. We have input devices like the keyboard, mouse, and scanner to put data into the system, and output devices like the monitor, speakers, and even modern 3D printers to retrieve our processed results. At the heart of the system is the Central Processing Unit, or CPU. Often called the brain of the computer, it contains the arithmetic logic unit for calculations and the control unit to manage instructions. It also has tiny local memory spaces called registers. Computers didn't always look like laptops. The evolution started as early as 500 BC with the manual abacus. Then came mechanical calculators like the Pascaline in 1642. Charles Babbage's analytical engine in 1834 laid the groundwork, and the invention of the transistor in 1947 changed electronics forever. A major breakthrough was the von Neumann architecture. Before this, machines had to be rewired to run new programs. Von Neumann introduced storing both the data and the programs together in memory. The ENIAC became the first programmable computer based on this architecture. As technology advanced, we grouped more transistors together into integrated circuits. Look at Moore's law. It predicted exponential growth in transistor density. We went from large-scale integration to super-large-scale integration, vastly increasing power while shrinking the actual physical size of computers. Now, let's talk about computer memory. Computers only understand binary digits, 0 and 1, known as bits. A group of 4 bits is a nibble, and 8 bits make a byte. This scales up massively from kilobytes to megabytes, all the way to massive yottabytes. There are different types of memory. Primary memory must load your program and data before the CPU can process them. RAM, or random access memory, is volatile. It temporarily stores active data while the power is on. ROM, or read-only memory, is non-volatile, storing permanent startup instructions for the computer. Between the blazing fast CPU and the slower primary memory sits cache memory. This is a very high-speed vault that stores frequently accessed data, which prevents the CPU from waiting around and greatly speeds up operations. Since primary memory is small and often volatile, we need secondary memory for long-term storage. This is non-volatile and has massive capacity. Examples you've used include hard disk drives, solid-state drives, pen drives, and CDs. How does data travel between all these parts? Through physical wires called system buses. We use a data bus to transfer actual data, an address bus to pinpoint memory locations, and a control bus to send synchronization signals across the motherboard. Let's revisit the brain. What are microprocessors? In modern computers, the entire CPU is fit onto a single microchip called a microprocessor. Driven by millions of tiny resistors and transistors, it processes millions of instructions in a mere millisecond. When comparing microprocessors, we look at several specifications. Word size is the maximum number of bits it can process at once, like 64-bit systems. Clock speed dictates how fast it executes, measured in gigahertz. And cores represent independent units, which is why we have dual-core or octa-core chips. You will also hear about microcontrollers. Unlike a microprocessor that just holds a CPU, a microcontroller also embeds RAM, ROM, and peripherals all onto one small chip. These are perfect for repetitive, specific tasks like running your washing machine or microwave. Moving from hardware to content. What is the difference between data and information? Data refers to raw, unorganized facts and symbols. When that data is processed and structured to provide meaning, it becomes information. Understanding this shift gives us knowledge. Data comes in different types. Structured data follows strict tabular formatting. Think spreadsheets, where it's easy to search and sort. Unstructured data is exactly the opposite. Images, videos, and large text documents do not follow a simple, predictable table. Between those two is semi-structured data. This type doesn't use rigid tables, but instead relies on internal tags to separate elements. Great examples of this are HTML web pages, email documents, and CSV files. Data has a life cycle. It starts with data capturing, using keyboards or barcode scanners. Next is storage, housing the data on local hard drives or massive cloud remote servers. Finally, retrieval is the process of efficiently searching and fetching that stored information when needed. What happens when you delete data? Deleting typically just marks that memory space as empty without instantly overwriting the physical bits. This means accidental losses can sometimes be reliably recovered. Because of this, using secure digital shredding is crucial before tossing out old storage devices. We've covered hardware and data, but what controls it? Software. This refers to the invisible sets of coded instructions that make computer hardware operational. They must work together perfectly. Software is broadly categorized into system software, application software, and programming tools. System software runs the background components. Operating systems are the core managers like Windows, Linux, or Android. System utilities handle maintenance like antivirus or disk defragmentation. And device drivers act as specific translators for your hardware peripherals. Humans write code in high-level languages, but computers only read zeros and ones. So, we need language translators. Assemblers translate assembly language. Compilers translate an entire high-level program at once, while interpreters translate and execute code line by line. Next is application software, which you use every day. General-purpose apps include web browsers and word processors. Customized software is tailor-made for specific companies. Additionally, you can find FOSS, free and open-source software, available to the public for free, unlike paid proprietary software. Finally, let's dive into the core functions of an operating system. It handles process management for background multitasking. Memory management dynamically allocates RAM on the fly, and file and device management ensures your data is secure and hardware communicates flawlessly. Thank you for joining Chapter 1. Welcome to Chapter 2. Today, we focus on encoding schemes and number systems, diving deep into how a computer handles human inputs. Have you ever wondered what exactly happens when you press A on your keyboard? The computer intercepts that physical action and translates it via internal mapping to a predefined code. This process is called encoding. It's the mandatory mechanism of converting human data into an equivalent cipher so that multiple distinct hardware brands function seamlessly. Historically, we standardized this using ASCII. Standing for American Standard Code for Information Interchange, it was developed in the early 1960s to completely unify digital communications. ASCII originally dedicated exactly 7 bits of memory per character. This mathematically allows for 128 unique combinations, which beautifully maps all English letters and standard punctuation. But what about global computing? ASCII famously lacked the memory addresses to support massive international character sets, severely limiting non-English developers. In response, India developed I in the 1980s. Leveraging an expanded 8-bit architecture, this Indian script format allowed 256 unique regional script characters to process accurately. ICE cleverly retains the original 128 ASCII codes at the bottom for normal English functionality, while reserving the upper half strictly for linguistic regional symbols known as aksharas. Today, we just use Unicode. This incredible global standard replaces all older fragmentation by assigning a unique numerical string to literally every written character on the entire planet. Unicode is fully compatible backwards with ASCII and deployed universally in modern web formats like UTF-8, UTF-16, and UTF-32 depending on memory requirements. Now that we've encoded letters into code arrays, how do hardware systems interpret those numbers mathematically? Let us introduce strict number systems. Computing utilizes positional number systems. This means a symbol's numeric value is governed totally by its physical position in the chain, multiplying exponentially the further left it sits. As humans, we naturally count using the decimal number system, or base 10. Leveraging precisely 10 numerical digits, it scales natively by multiplying powers of 10. Computers do not. Processors operate using exclusively binary, or base 2. By reducing variables to just ones and zeros, physical logic gates can calculate using high and low electrical voltages. This hardware limitation dictates software completely. The CPU cannot interpret 10 separate states seamlessly, so mapping logic states as pure binary is the safest approach to robust hardware architecture. Unfortunately, staring at screens filled exclusively with millions of binary zeros and ones causes intense human error. Thus, engineers frequently compress this data into octal systems, or base 8. Octal natively limits values between 0 and 7. Mathematically, any three binary data bit subsets compress with absolute perfection into a single, clean octal digit. However, modern 64-bit processing relies almost entirely on the hexadecimal number system. This is base 16, adding alphabet letters A through F beside our normal numerical digits. Hex is incredibly powerful. Because 16 is 2 to the power of 4, every sequence of 4 individual binary bits compresses seamlessly into one highly efficient hex alphanumeric symbol. You see hex all the time, from allocating explicit hexadecimal memory addresses in computer RAM to encoding 6-digit RGB color matrices commonly used in web design. Due to overlapping architectures, computer science requires fast base conversion techniques, methods to effortlessly translate massive integer chunks correctly between these variable bases. If you want to map base 10 into binary, you repeatedly perform successive division by 2, tracking every remainder bit and stacking them perfectly in reverse chronological order. Conversely, to unwrap binary data back into human decimal, you use positional multiplication. You literally multiply every 1 or 0 by its corresponding exponential positional value over the grid. When dealing with fractional components behind decimal dots, engineers carefully manipulate these conversion algorithms using successive multiplication frameworks instead of strict division. That wraps up Chapter 2. Encoding's perfectly standardized alphabets and positional number systems construct mathematical data states using native binary architecture frameworks. Thank you. Welcome to Chapter 3. Now we will move aggressively beyond foundational hardware into fascinating emerging trends heavily reshaping computer science. The most rapidly discussed field is artificial intelligence. AI is explicitly the grand scientific endeavor to simulate true cognitive reasoning and complex real-time decision-making capabilities using exclusively digital circuits. However, achieving AI fundamentally relies on machine learning. Instead of massive human engineering teams mapping out thousands of static logic rules, ML models autonomously refine their own predictions actively by analyzing heavy, unstructured data pipelines. Once supplied with massive external training sets of organized variables, they quickly run recursive testing phase deployments to naturally adjust internal parameters precisely against complex errors. But machines need natural data natively. Natural language processing acts as a dense algorithmic bridge to accurately organize complex human voice commands directly into strict machine operations, seamlessly. Furthermore, massive disruption is occurring visually via immersive experiences. Programmers are moving aggressively past extremely flat visual rendering and injecting dynamic data deeply into interactive, fully 3D spatial configurations. Specifically, virtual reality utterly strips away external visual input, utilizing entirely isolated digital headsets to fully immerse the user safely within intensely realistic digital environmental logic. Augmented reality, however, keeps the user visually anchored entirely. It leverages clever heads-up hardware components to layer incredibly dense digital mapping statistics transparently over normal spatial reality seamlessly. We also map massive software logic physically outside the server. Robotics heavily intertwines cutting-edge computer processing safely into precisely tooled mechanical components, saving extreme human labor aggressively in high-danger industrial factory ecosystems. Current-generation robots span dynamically from highly intelligent autonomous tracking drones used heavily in military logic setups to sophisticated multimodal humanoid systems utilizing artificial neural circuits actively. To power massive artificial intelligence parameters correctly requires big data. Globally, computers now aggressively process heavily over 2.5 quintillion massive bytes of variable media interactions per unique day. Traditional SQL crashes completely against this pressure. Professionals define true big data constraints by mapping the 5 versus war. The first is volume, a brutally literal metric measuring the massive physical raw size of overlapping datasets securely. Velocity denotes precisely the hyper-accelerated momentum rate at which this unstructured chaotic info generates massively across global public networks sequentially. Variety represents precisely the complex structural nightmare generated by stacking completely incompatible video feeds closely against messy text logs natively simultaneously. Veracity indicates strict bias and noisy corruption probability. Value defines strictly how lucrative these hidden internal trends are, fundamentally, when extracted algorithmically securely by global enterprise. Tremendous data generation overlaps closely with the Internet of Things logic loops. The IoT massively networks previously dumb household electronics efficiently with highly robust digital Wi-Fi transmission chips globally. To allow completely varying smart fridges effectively to securely talk to entirely random smart cars simultaneously, engineers dynamically embed extensive Web of Things protocols to normalize software connectivity limits securely. Inside these IoT devices sit incredible advanced smart sensors perfectly calibrating localized inputs. Your phone's accelerometer or active digital gyroscope precisely reads massive environmental context natively continuously. Connecting millions of these active sensors constructs entirely what we actively term smart cities seamlessly. These networks dynamically trigger vast municipal alarms, accurately tracking precise bridge vulnerabilities cleanly, automatically. How do developers realistically operate inside these immense storage constraints? Cloud computing totally alleviates internal server needs closely by massively outsourcing data pipelines securely across heavily redundant enterprise networking data centers. Renting out raw digital architecture directly securely defines IaaS, or infrastructure as a service natively. You strictly just rent extreme multi-terabyte drives cleanly without massive initial mechanical hardware purchases. Alternatively, you actively subscribe to platform tools perfectly like hosted Python instances via PaaS natively, or purely consume final browser interfaces completely like Google Docs aggressively via SaaS. Cloud frameworks are strictly centralized logic. Grid computing operates contrarily entirely. It stitches completely randomized physical user laptops dynamically into entirely distributed supercomputers capable flawlessly of cracking ultra-dense mathematical theorems collaboratively. This heavy decentralization actively powers massive blockchain setups seamlessly. Massive global ledgers inherently resist deep hacking corruption exactly by relying inherently on complex multi-node peer algorithmic verifications completely uniformly. In Chapter 3, we observed actively exactly how entirely unbridled AI integrations strongly couple cleanly tightly with immense data environments natively. See you in the next exciting sequence. Welcome to Chapter 4. Today we explore Introduction to Problem Solving. We will learn exactly how computers automate massive tasks and act as the foundation of modern software engineering. What exactly is problem solving? Computers themselves possess zero creativity. They cannot organically solve anything. They require unbelievably precise, step-by-step human instructions mapped mathematically to function. Professional engineering breaks problem solving into 4 rigorous steps: analyzing the problem structurally, developing a conceptual algorithm, actual coding, and finally, testing and debugging the logic tightly. Step 1 is analysis. You must intimately understand the core issues before writing any syntax. Developers meticulously isolate the explicit inputs they have and mathematically define the exact outputs they need. This enforces the famous computing principle of GIGO, garbage in, garbage out. A computer executes math flawlessly. If your underlying business logic is flawed, the compiler simply calculates that failure flawlessly. Next, we develop an algorithm. You never type code blind. You devise a complete solution offline first. It acts identically to a highly detailed culinary recipe tailored strictly for digital hardware execution. Once the algorithm is complete, phase 3 is coding. Here, a developer translates human abstraction tightly into a high-level language like Python, forcing the logic through a compiler or interpreter. Phase 4 is testing. The raw code must safely execute across wild variables without crashing servers. Software companies deploy brutal unit testing, safely isolating hidden syntactic syntax bugs continuously. Let us look intimately at algorithms again. By definition, an algorithm must contain a heavily finite sequence of concrete mechanical manipulations designed cleanly to achieve an explicit output state natively. Consider solving the greatest common divisor mathematically. You design an algorithm cleanly outlining explicitly. Step 1. Generate denominators internally. Step 2. Isolate and match the max variable natively. Algorithms are judged on three brutal scales. Precision eliminates ambiguity entirely. Finiteness absolutely guarantees the math terminates natively. And uniqueness guarantees identical outputs mathematically for perfectly uniform inputs. To visualize deeply complicated algorithms, engineers heavily deploy structured abstract representations safely. Most universally, teams rely entirely on graphical flowcharts closely alongside human-readable pseudocode structurally. Flowcharts are incredibly robust visual topological diagrams globally. Built carefully using standardized connecting boxes creatively, they dynamically map the exact sequence of logical data flow seamlessly natively. These standardized icons carry heavy significance globally. Oval terminators cleanly signal program execution stops. Parallelograms effectively snatch human inputs. Rectangles perform background math computations entirely natively. If shapes disrupt your creative flow cleanly, teams utilize pseudocode. Literally translating to not real code, pseudocode maps complex architectural variables actively into extremely rigid standard English vocabulary securely. Pseudocode safely exposes dense logic flaws dynamically, incredibly early during development cycles, cleanly entirely without requiring junior developers, securely to wrestle aggressively heavily with punishing compiler syntax loops. To successfully assemble pseudocode safely, you must strictly master the flow of control logic inherently. Core programming seamlessly rests across exactly three main pillars internally: sequence natively, selection dynamically, and repetition structurally. First, sequence cleanly describes standard computing. Abstract commands structurally execute fiercely top to bottom natively, line by line perfectly, without aggressively skipping lines, seamlessly inside the compiler. However, massive reality forces dynamic selection cleanly. Known explicitly as branching inherently, it enables the computer seamlessly to instantly evaluate external variables, natively dynamically heavily routing data flawlessly down alternate paths securely. Encode dynamically, selection manifests securely as the if and else statement framework structurally. Hardware securely tests a binary condition creatively. If distinctly true, run branch A cleanly. Otherwise, inherently route gracefully to B. You cleanly stack these loops seamlessly utilizing else-if constructs perfectly securely. The CPU aggressively probes vertically dynamically until exactly one algorithmic variable creatively triggers securely, true heavily gracefully. Finally, safely we tackle repetition, cleanly, intuitively, natively. Commonly effectively labeled looping dynamically, it fiercely instructs software gracefully seamlessly to actively execute exactly the same identical logic cluster, safely hundreds of times successfully. A pristine loop natively tracks its structural iterations, securely, safely tightly, using purely an internal count variable elegantly. Once heavily the target count correctly reaches equality, natively, the loop creatively shatters safely, allowing code to advance effectively. If engineers safely bungle that exit parameter cleanly, an infinite loop securely fatally crashes the entire architecture gracefully. The engine precisely executes completely, endlessly creatively, locking the massive CPU dynamically permanently. Wrapping Chapter 4 accurately securely. Programming elegantly is precisely not simply coding natively safely, but deeply mapping clean visual algorithms accurately, gracefully, leveraging repetition effectively securely. Welcome to Chapter 5. Getting started with Python. In this chapter, we make the exciting leap from designing algorithms on paper to writing real code. Python is one of the most widely used programming languages in the world today. Computers only understand machine language made up of zeros and ones. Since writing in binary is impractical for humans, we use high-level languages like Python that are closer to English. A language translator then converts our code into machine language. There are two types of translators: compilers and interpreters. A compiler translates the entire program at once before running it, while an interpreter translates and executes one statement at a time. Python uses an interpreter, so errors are caught immediately line by line. Python has several powerful features. It is free and open source, highly portable across Windows, Mac, and Linux, and easy to learn due to its clean, readable syntax. Python is also case-sensitive, so the word number and number are treated as completely different identifiers. Python can be used in two execution modes: Interactive mode lets you type and run one statement at a time directly at the prompt, which is great for quick experiments. Script mode lets you write a full program in a file and run it all at once. In interactive mode, you see the three greater than symbols, the Python prompt. You type an instruction and press enter, and the result appears immediately. This mode is perfect for testing small snippets of code, but cannot save your work for later use. Script mode is used for writing complete programs. You write your code in a file saved with the .py extension, then run it using IDL or from the command line. This is the approach used in professional software development. Python has a set of reserved words called keywords that have fixed meanings in the language. You cannot use these as variable names. Examples include true, false, if, else, for, while, break, and return. Python is case-sensitive, so these keywords must be written exactly as shown. Identifiers are the names we give to variables, functions, and other entities in our program. An identifier must start with a letter or underscore, cannot start with a digit, cannot be a keyword, and cannot contain special symbols like the @ sign or hash. A variable is a named memory location that holds a value. In Python, you create a variable simply by assigning a value to it using the equals sign. For example, writing price equals 987 creates a variable named price and stores the number 987 in it. Comments are lines in the code that the interpreter ignores completely. They are written using the hash symbol and are meant for human readers to understand the code. Good commenting practice is essential when working in teams or revisiting code after a long time. In Python, everything is an object. Every value, whether a number or a string, is stored as an object in memory. Each object has a unique identity that can be checked using the ID function. Two variables pointing to the same value will often share the same identity. Python supports several numeric data types. The int type stores whole numbers like 5 or -12. The float type stores decimal numbers like 14.23. The complex type stores numbers with a real and imaginary part, such as 3 plus 4j. Boolean data type has only two values, true and false. It is a subtype of integer, where true equals 1 and false equals 0. Booleans are fundamental for writing conditions in if statements and controlling the flow of a program. Sequence data types store ordered collections of elements where each element is accessed using an index starting from 0. Python has three main sequence types: strings, lists, and tuples. Each serves a different purpose in storing and organizing data. A string is a sequence of characters enclosed in single or double quotes. Strings are used to store text data like names, messages, or sentences. You cannot perform arithmetic on strings, but Python provides many powerful string manipulation operations. A list is a mutable, ordered collection of elements enclosed in square brackets. Lists can store elements of different data types together, including integers, floats, and strings. You can add, remove, or change elements in a list after it has been created. A tuple is similar to a list, but is enclosed in parentheses and is immutable, meaning its elements cannot be changed after creation. Tuples are typically used for data that should remain constant, such as coordinates or fixed configuration values. A set is an unordered collection of unique elements enclosed in curly braces. Sets automatically remove duplicates, making them ideal for operations like finding common elements between two groups or checking membership efficiently. The none type represents the absence of a value. It is not the same as 0 or false. None is commonly used when a variable needs to be declared before a value is available, or when a function does not return any result. Dictionaries are a mapping type that store data as key-value pairs inside curly braces. Each key is unique and maps to a specific value. For example, a dictionary could store a student's name as the key and their marks as the value, enabling very fast lookups. One of the most important concepts in Python is the distinction between mutable and immutable data types. Mutable types can be modified after creation, while immutable types cannot. Understanding this affects how Python manages memory and how data is shared between variables. Mutable types, like lists and dictionaries, can be changed in place. If you modify a list, the change happens directly in memory without creating a new object. This means multiple variables pointing to the same list will all see the change. Immutable types like integers, strings, and tuples cannot be changed after creation. When you appear to modify an integer variable, Python actually creates a new object in memory. This is why changing one integer variable does not affect another that had the same value. In summary, Chapter 5 introduced us to the Python programming language, including how to run programs in interactive and script modes, the key data types like int, float, string, list, tuple, and dictionary, and the crucial difference between mutable and immutable types. We are now ready to learn how to control program flow. Welcome to Chapter 6, Flow of Control. So far, our programs have executed line by line from top to bottom. In this chapter, we learn how to make programs branch based on conditions and repeat actions using loops. The flow of control refers to the order in which statements in a program are executed. By default, Python follows sequential execution, one statement after another. But real-world problems often require decisions and repetition, so Python provides two powerful control structures for this. Sequence is the simplest flow of control. Statements execute in the exact order they are written, one after another. Think of a recipe. You add ingredients in a fixed order, and skipping or reordering steps changes the outcome entirely. Selection, also called decision-making, allows a program to choose between different paths based on a condition. If you're choosing which road to take based on traffic, that is selection. In Python, this is implemented using the if, else, and elif statements. The if statement is the most basic form of selection. You write a condition after the word if, followed by a colon. If the condition evaluates to true, the indented block of code below it executes. For example, if age is greater than or equal to 18, print eligible to vote. The if-else statement gives us two execution paths. If the condition is true, the if block runs. If it is false, the else block runs instead. This is like a fork in the road where you must always take one of the two paths. When you have more than two possibilities, you use elif, which stands for else if. Python checks each condition from top to bottom, and as soon as one is true, it executes that block and skips all the rest. The final else acts as a catch-all for any remaining case. Nested if statements occur when you place an if block inside another if or else block. This allows you to handle complex multi-level conditions. For example, in a calculator program, first check which operator was entered, then check for special cases like division by zero. Indentation is how Python defines blocks of code. Unlike most languages that use curly braces, Python uses whitespace. All statements belonging to the same if or else block must be indented by the same amount. Getting this wrong causes an indentation error. The standard convention is to use 4 spaces for each level of indentation. Proper indentation is not just a syntactic requirement in Python, it actually makes code easier to read and understand. It is one of the features that makes Python code look clean and organized. Repetition or looping is the third pillar of flow of control. It allows a block of code to execute multiple times without writing it repeatedly. Imagine printing the first 100,000 natural numbers. With a loop, you need just 3 lines of code. The for loop is used to iterate over a sequence of values. The loop variable takes on each value in the sequence one at a time, and the loop body executes once per value. The number of iterations is typically known before the loop starts. You can use a for loop with strings, lists, and other sequences. Iterating over the string, Python prints each letter on a separate line. Iterating over a list of numbers processes each number one by one. This makes for loops extremely versatile. The range function is a built-in function that generates a sequence of integers. It takes up to 3 arguments: start, stop, and step. The stop value is not included in the sequence. For example, range of 2 to 10 gives 2, 3, 4, up to 9. Combining 4 with range is extremely common. For example, for num in range 5, we'll iterate with num taking values 0, 1, 2, 3, and 4. You can also use a negative step to count down. Range is only used in for loops and always produces integers. The while loop repeats a block of code as long as its condition remains true. Unlike the for loop, you use a while loop when the number of repetitions is not known in advance and depends on some condition being met during execution. A while loop requires 3 things. First, initialize a control variable before the loop. Second, write a condition that uses this variable, and third, update the variable inside the loop body. If you forget to update the variable, the condition never becomes false and you get an infinite loop. Use a for loop when you know how many times to repeat in advance. Use a while loop when the repetition depends on a condition that changes during execution. Both loops can solve the same problems, but choosing the right one improves code clarity. The break statement immediately exits the nearest enclosing loop. When Python encounters a break, it stops the loop and jumps to the first statement after the loop. This is useful for searching. Once you find what you are looking for, there is no need to continue. The continue statement skips the rest of the current iteration and jumps back to the beginning of the loop for the next iteration. Unlike break, the loop does not end. It just skips what would have happened for that one particular cycle. A nested loop is a loop placed inside another loop. The inner loop completes all its iterations for every single iteration of the outer loop. If the outer loop runs 10 times and the inner loop runs 10 times, the inner body executes 100 times in total. A classic example of nested loops is printing a multiplication table. The outer loop controls the row number and the inner loop controls the column. For each row, the inner loop multiplies the row number by each column number from 1 to 10. An infinite loop occurs when the loop condition never becomes false. Writing while true with no break statement is an intentional infinite loop used in servers and games. An accidental infinite loop, caused by forgetting to update the control variable, will freeze your program. A practical example combining all these concepts is a simple calculator. The program uses if, elif, else to select the correct arithmetic operation, nested conditions to handle division by zero, and could use a while loop to allow multiple calculations before quitting. To summarize Chapter 6, we mastered the 3 flow control structures: sequence for step-by-step execution, selection using if, elif, else for decision-making, and repetition using for and while loops. We also learned break and continue to fine-tune loop behavior. These are the building blocks of all real programs. Welcome to Chapter 7, Functions. As programs grow longer, they become harder to read and debug. Functions solve this by letting us break a big problem into smaller, self-contained, named pieces of code that each solve one specific task. Functions provide 4 major benefits. First, they make code more readable. Second, they reduce code length because the same logic does not need to be written multiple times. Third, they make debugging easier. And fourth, they enable team collaboration by allowing different developers to work on different functions. Modular programming is the technique of dividing a program into separate, independent blocks. Consider a tent manufacturing company computing costs. Instead of one long program, they break it into 3 functions: one for the cylindrical area, one for the conical area, and one for the post-tax price. Python has 3 categories of functions. Built-in functions like print and len are always available. Standard library functions like math.th must be imported, and user-defined functions are written by you to solve problems specific to your program. To define a function in Python, start with the keyword def, followed by the function name, parentheses, and a colon. The body of the function is the indented block that follows. Importantly, a function must be defined before it is called anywhere in the program. Defining a function does not execute it. The code inside the function only runs when you call the function. To call a function, write its name followed by parentheses. For example, writing addNum triggers the execution of the addNum function. Parameters are variables listed in the function definition that act as placeholders for incoming data. Arguments are the actual values passed during the function call. When you call sum squares of 5, the value 5 is the argument that gets assigned to the parameter n inside the function. A function can accept multiple parameters separated by commas. For example, def fullname accepts first and last as 2 parameters. When calling the function, you provide 2 arguments in the same order: first name, then last name. The function then concatenates them. A default parameter has a predefined value that is used when the caller does not provide that argument. For example, def mixed fraction with dno equal to 1 means that if you call mixed fraction of 9, dno automatically takes the value 1 without you needing to specify it. There is an important rule for default parameters. They must always appear after all non-default parameters in the function header. Writing def calc interest with principal having a default before rate, which has no default, is incorrect and will cause an error. The return statement serves two purposes. It sends a value back to the caller, and it immediately transfers control back to the calling code. Functions without a return statement are called void functions and implicitly return the special value none. Consider the function calcpow that accepts a base and an exponent, computes the result, and returns it. The calling code stores the return value in a variable, answer equals calcpow of 5 and 4. The return value sit5 is now stored in answer and can be used freely. Based on parameters and return values, Python functions come in four forms. A function can have no arguments and no return, no arguments but a return, arguments but no return, or both arguments and a return value. The right form depends on what the function needs to do. The flow of execution changes when functions are involved. When Python hits a function definition, it remembers it but does not run it. When it encounters a function call, control jumps into the function. After the function completes, control returns to the line right after the call. Scope refers to the region of a program where a variable can be accessed. A local variable is created inside a function and only exists while that function is running. A global variable is defined outside all functions and can be accessed anywhere in the program. Local variables are created fresh each time a function is called and destroyed when the function ends. This means two separate calls to the same function do not share variable memory. Whatever you compute inside a function stays inside unless you explicitly return it. Global variables are accessible from anywhere in the program, including inside functions. However, if you try to modify a global variable inside a function without declaring it, Python treats it as a new local variable instead. The function sees the global value but cannot change it without explicit declaration. To modify a global variable inside a function, you must declare it using the global keyword. Writing global x at the top of a function tells Python that x refers to the global variable, not a new local one. While this works, overusing global variables makes code harder to understand. Python comes with a rich standard library containing hundreds of pre-built functions organized into modules. To use them, you first import the module. For example, writing import math gives you access to mathematical functions like square root, power, floor, ceiling, and constants like pi. There are two ways to import. Writing import math means you call functions as math.scort. Writing from math import scort means you can call scort directly without the module name prefix. The random module provides random.randint to generate random integers between two values. The math module contains many useful functions. Math.scort returns the square root. Math.pow raises a number to a power. Math.floor rounds down to the nearest integer, and math.ceil rounds up. The constant math.pi gives you the value of pi to many decimal places. Python also provides built-in conversion functions that do not require importing. The function len returns the length of a string or list. The function str converts a number to a string. The function int converts a string or float to an integer. The advantages of user-defined functions are significant. Reusability means you write the logic once and call it many times. Readability means the program is organized into clearly named sections. And maintainability means you fix a bug in one place and it is fixed everywhere the function is used. Recursion is a technique where a function calls itself. A recursive function must have a base case that stops the recursion, otherwise it runs forever. The classic example is factorial. Factorial of n equals n multiplied by factorial of n minus 1, with factorial of 0 equal to 1 as the base case. To summarize Chapter 7, functions are named blocks of reusable code defined with def. They accept parameters, optionally return values, and have their own local scope. Python's standard library provides powerful ready-made functions through importable modules. Functions are essential for writing organized, efficient, and maintainable programs. Welcome to Chapter 8, Strings. Strings are one of the most versatile and commonly used data types in Python. They are used to store and process text, whether it's a single character, a word, a sentence, or an entire paragraph. A string is a sequence of Unicode characters. You create a string by enclosing characters in single, double, or triple quotes. Whether you use single or double quotes does not matter, as long as you are consistent. Triple quotes are used for multi-line strings. Triple quoted strings can span multiple lines without needing any special escape characters. They are commonly used for documentation strings, also called doc strings, which describe what a function or module does. The new line characters in the text are preserved inside the string. Every character in a string has a position called an index. Indexing starts at 0 from the left, so the first character is at index 0, the second is at index 1, and so on. Accessing an index beyond the length of the string raises an index error. Python also supports negative indexing, which lets you access characters from the right end. Index -1 refers to the last character, -2 to the second last, and so on. This is particularly useful when you need the last character but do not know the length of the string. Slicing extracts a portion of a string using the syntax string of start: stop: step. The start index is included, but the stop index is excluded. For example, slicing the string hello world from index 0 to 5 gives you hello, extracting just the first 5 characters. Slicing is very flexible. Omitting the start means beginning from the first character. Omitting the stop means going all the way to the end. Using a step of 2 extracts every second character. And using a step of -1 reverses the entire string. An important property of strings is that they are immutable. Once a string is created, its characters cannot be changed. Attempting to assign a new character to an index like str1 at 0 equals j raises a type error. To change a string, you must create a new one. The plus operator concatenates or joins 2 strings together. Hello plus a space plus world produces hello world. Both operands must be strings. If you try to concatenate a string with an integer, Python raises a type error. You must first convert the integer to a string using str. The asterisk operator repeats a string a given number of times. Hey times 3 gives ha ha ha. The in operator checks if one string is a substring of another. The string Elwin hello returns true. The not in operator does the opposite check. To traverse a string means to process each character one at a time. The simplest way is a for loop. For ch in the string Python, the loop variable ch takes the value p, then y, then t, and so on each iteration. You can also use range and len to traverse by index. Strings support comparison operators like equals, not equals, less than, and greater than. Comparison is done character by character based on Unicode values. Since the letter A comes before B in Unicode, comparing apple with banana tells us apple is less than banana. Python's string methods make text processing very powerful. The upper method converts all characters to uppercase, while lower converts to lowercase. The capitalize method makes only the first letter uppercase, and the title method capitalizes the first letter of every word. For searching within strings, count returns how many times a substring appears. The find method returns the index of the first occurrence and returns -1 if not found. The index method works the same way, but raises a value error if the substring is absent. The replace method substitutes all occurrences of one substring with another. The strip method removes whitespace from both ends of the string, which is very useful when processing user input. lstrip removes only from the left and rstrip only from the right. The split method breaks a string into a list of substrings at each occurrence of a separator. Splitting the string a, b, c using comma as the separator gives the list a, b, c. The join method does the reverse. It joins a list of strings into one single string using a specified separator. Python provides useful checking methods. Isalpha returns true if all characters in the string are alphabetic. Isdigit returns true if all characters are numeric digits. Isalnum returns true if all characters are either letters or digits with no spaces or punctuation. The starts with and ends with methods check the beginning and end of a string respectively. For example, you might check if a file name ends with .py to confirm it is a Python script. These methods return true or false and are cleaner than using slicing for this purpose. The built-in len function returns the total number of characters in a string. Len of hello returns 5. Len of an empty string returns 0. Knowing the length is essential for loop-based traversal and for preventing index out-of-range errors when slicing. String formatting allows you to embed variable values inside a string. The format method uses curly braces as placeholders. F-strings, available from Python 3.6, are even more convenient. You prefix the string with F and write variable names directly inside curly braces. Escape sequences are special character combinations beginning with a backslash. \n creates a new line, \t creates a tab, and two backslashes produce a literal backslash character. These are used when you need to include characters in a string that would otherwise be interpreted differently. Since strings are sequences, several built-in sequence functions work on them. The min function returns the character with the smallest Unicode value, and max returns the largest. The sorted function returns a new sorted list of all the characters in the string. A palindrome is a string that reads the same forwards and backwards, like race car. To check for a palindrome, simply compare the string with its reverse. The reverse is obtained using slicing with a step of -1. If they are equal, the string is a palindrome. A common string processing task is counting vowels. You traverse the entire string character by character using a for loop. For each character, you check if it exists in the string of vowels A, E, I, O, U in both uppercase and lowercase. Each match increments a counter. Chapter 8 gave us a thorough understanding of strings in Python. Strings are immutable sequences supporting indexing, slicing, concatenation, and repetition. Python's rich set of string methods, including upper, lower, find, replace, split, and join, make text processing elegant and powerful. Welcome to Chapter 9, Lists. Lists are one of the most important and widely used data structures in Python. They allow us to store a collection of items in a single variable, where each item can be of a different type. A list is an ordered sequence of elements enclosed in square brackets and separated by commas. What makes lists special is their flexibility. A single list can hold integers, floats, strings, and even other lists all at the same time. Like strings, list elements are accessed using indices starting from 0. You can create a list in several ways. An empty list uses just two square brackets. A list of numbers, a list of strings, or a mixed list can all be created by placing the elements inside brackets separated by commas. A nested list, which is a list inside a list, is also perfectly valid. Accessing elements works the same as with strings. The first element is at index 0, and negative indices count from the right. For example, index -1 gives the last element. Trying to access an index beyond the list's length raises an index error. The most important difference between lists and strings is that lists are mutable. You can change their contents after creation. Assigning a new value to an index like list1 at index 3 equals black directly modifies the element at that position. This makes lists ideal for data that changes over time. The plus operator concatenates two lists. Joining the list of odd numbers and the list of even numbers gives a combined list. Note that the original lists are not modified. If you want to keep the merged result, you must assign it to a new variable. The asterisk operator repeats a list a given number of times. The in operator checks if an element exists anywhere in the list and returns true or false. The not in operator checks the opposite. These operators make searching and repetition concise and readable. List slicing works exactly like string slicing using start: stop: step. The stop index is excluded. You can extract a portion of a list, skip elements using a step, or create a reversed copy using a step of -1. Slicing always returns a new list. Traversing a list means visiting each element one by one. The simplest way is a for loop that iterates directly over the list. Alternatively, you can loop using range and the length of the list to access elements by index, which is useful when you need to know the position. The append method adds a single element to the very end of a list. The extend method adds all elements from another list one by one. The key difference is that append of a list within brackets creates a nested element, while extend flattens it and adds each item individually. The insert method takes two arguments, an index position and a value. It inserts the value at the given position, shifting all subsequent elements one place to the right. The count method returns how many times a specific value appears in the list. The index method returns the position of the first occurrence of a value. If the value is not found, it raises a value error. The remove method deletes the first occurrence of a specified value from the list. If the value appears multiple times, only the first one is removed. The pop method removes and returns an element. Without an argument, pop removes and returns the last element. With an index argument, it removes and returns the element at that position. The reverse method reverses the list in place, permanently changing the original order. The sort method arranges elements in ascending order by default and modifies the original list directly. Passing reverse equals true sorts in descending order. The built-in sorted function is different. It returns a new sorted list and leaves the original unchanged. Python has several built-in functions that work well with lists. Len returns the count of elements. Max and min find the largest and smallest values. Sum adds all numeric elements together. And the list function converts other sequences like ranges and strings into lists. A nested list is a list that contains other lists as its elements. This is used to represent two-dimensional data, like a matrix or a table. You access an element in a nested list using two indices. The first selects the inner list, and the second selects the element within it. Copying a list requires care. Writing list2 equals list1 does not create an independent copy. Both variables point to the same list in memory. Modifying list2 also modifies list1. To create a true separate copy, use slicing, the list function, or the copy method. When you pass a list to a function, the function receives a reference to the original list, not a copy. This means any changes the function makes to the list are reflected outside the function as well. This is called passing by reference and is different from how integers are passed. The del statement deletes elements from a list. You can delete a single element by index, a range of elements using slicing, or the entire list variable. After del list1, the variable no longer exists, and accessing it raises a name error. List comprehension provides a concise, readable way to create a new list. The syntax is an expression followed by a for clause and an optional if clause, all inside square brackets. For example, a list of squares can be created as x squared for x in range of 5, which gives 0, 1, 4, 9, and 16. Comparing lists and strings. Strings can only hold characters, while lists can hold any type. Strings are immutable. Lists are mutable. Both support indexing, slicing, and the in operator. But lists have many more built-in methods for adding, removing, and reorganizing data. Finding the maximum value in a list manually requires traversing the entire list and keeping track of the largest value seen so far. Start by assuming the first element is the maximum. Then compare each subsequent element. If a larger one is found, update the maximum. Python's max function does all of this automatically. Linear search is a basic algorithm to find a target value in a list. You check each element one by one from the beginning. If the element matches the target, you return its index. If you reach the end without finding it, you return -1 to indicate it was not found. Double sort is a simple sorting algorithm. It repeatedly compares adjacent elements and swaps them if they are in the wrong order. After each complete pass through the list, the largest unsorted element has moved to its correct final position. The process repeats until no more swaps are needed. Chapter 9 explored Python lists in depth. Lists are ordered, mutable sequences enclosed in square brackets that support indexing, slicing, and all major operations. Key methods include append, extend, insert, remove, pop, sort, and reverse. Lists are one of the most essential tools in any Python programmer's toolkit. Welcome to Chapter 10, Tuples and Dictionaries. This chapter introduces two more essential Python data structures. Tuples are like lists but immutable, and dictionaries store data as key-value pairs for fast, meaningful lookups. A tuple is an ordered sequence of elements that can be of different data types. Tuples are written with elements inside parentheses, separated by commas. You can store integers, floats, strings, and even lists inside a tuple. Like lists, elements are accessed using zero-based indexing. A very important rule: if you have a tuple with only one element, you must put a trailing comma after it. Writing round bracket 20, round bracket without a comma, makes Python treat it as an integer, not a tuple. Writing round bracket 20 comma round bracket correctly creates a single element tuple. Accessing tuple elements works exactly like lists. Use a positive index starting from 0 to access from the left, or a negative index starting from -1 to access from the right. You can also use slicing to extract a range of elements. An out-of-range index raises an index error. The most fundamental property of a tuple is that it is immutable. Once you create a tuple, its elements cannot be changed. Attempting to do so causes a type error. Because of this immutability, tuples are faster than lists and can be used as dictionary keys, which lists cannot. Tuples support the same operations as lists for reading data. You can concatenate two tuples with the plus operator, repeat a tuple with the asterisk operator, check membership using in and not in, and slice to extract a portion. All these operations return new tuples without modifying the originals. Tuple unpacking or assignment lets you assign several variables at once from a single tuple. Writing a comma b, comma c equals the tuple 10, 20, 30 assigns each value to its respective variable in one line. This is a very convenient Python feature used frequently in practice. Tuples have only two methods, count and index. The count method returns how many times a value appears. The index method returns the position of the first occurrence. Built-in functions like len, max, min, and sorted also work with tuples, though sorted returns a list as output. Nested tuples are tuples that contain other tuples as elements. This creates a multi-dimensional structure. To access an element in a nested tuple, you use two indices, the first to select the inner tuple and the second to select the element within it. When should you use tuples instead of lists? Use tuples for fixed collections that should not change, like the days of the week or coordinates. Tuples are slightly more memory efficient than lists. And crucially, tuples can serve as dictionary keys while lists cannot, because dictionaries require immutable keys. A dictionary is a collection of key-value pairs. Unlike sequences indexed by integers, dictionaries are indexed by keys, which can be strings, integers, or tuples. Dictionaries are written with key-value pairs inside curly braces, where each pair is separated by a colon. You can create a dictionary directly using curly braces with key colon value pairs, or using the dict function. An empty dictionary is created with just two curly braces. Keys in a dictionary must be unique and immutable. If you use the same key twice, the second value overwrites the first. To access a value in a dictionary, use its key inside square brackets. For example, student at name gives a run. The get method is safer because it returns none or a default you specify if the key does not exist, instead of raising a key error like direct square bracket access would. Dictionaries are mutable. You can change an existing value by assigning a new value to its key. You can add a completely new key-value pair simply by assigning a value to a key that does not yet exist. And you can delete a key-value pair using the del statement. The in operator on a dictionary checks for key existence, not value existence. Writing name in student asks whether name is one of the keys. The len function returns the total number of key-value pairs. Dictionaries do not support slicing or the plus concatenation operator. You can traverse a dictionary in three ways. A standard for loop iterates over the keys. Calling dict.keys explicitly returns a view of all keys to loop over. Calling dict.values gives access to all values. And dict.items returns each key value pair as a tuple, which can be unpacked in the loop. The keys, values, and items methods return special view objects. These views are not separate copies. They reflect the current state of the dictionary. If you add or remove a key after creating a view, the view automatically shows the updated state. The update method merges another dictionary into the current one. If a key exists in both dictionaries, the value from the other dictionary overwrites the original. The get method with a default value is the safe alternative to direct key access when you are not sure if a key exists. The pop method removes a key and returns its value. If the key does not exist and no default was provided, it raises a key error. The clear method removes all key value pairs at once, leaving an empty dictionary. The dictionary itself still exists. It is just empty. A practical use of dictionaries is counting word frequencies. For each word in a sentence, check if it is already a key. If it is, add one to its count. If it is not, add it as a new key with a count of 1. This builds a complete frequency map in a single pass through the text. A nested dictionary has dictionaries as values. For example, a school dictionary might have class names as keys and each class's section details as nested dictionaries. To access a nested value, chain two square bracket accesses. School at Class 1 at A gives the number of students in Class 1 Section A. Lists use integer positions to identify data, which can be confusing. Dictionaries use meaningful keys, making code self-documenting and easier to understand. Dictionary lookups are also extremely fast. They are performed in constant time, regardless of how many keys the dictionary has. Just like lists, assigning one dictionary variable to another does not copy it. Both point to the same dictionary. To create an independent copy, use the copy method. For dictionaries with nested objects, use copy.deepcopy from the copy module to ensure a completely independent duplicate. Let us compare tuples and dictionaries. A tuple like Arun, 1, 95 stores data positionally, requiring you to remember that index 2 means marks. A dictionary like name Arun, roll 1, marks 95 is self-explanatory. Dictionaries are more readable, while tuples are more compact and memory efficient. Chapter 10 covered two fundamental data structures. Tuples, immutable ordered sequences in parentheses, are ideal for fixed, unchanging data and can serve as dictionary keys. Dictionaries, mutable key-value mappings in curly braces, provide fast, readable access to structured data. Together with lists, these form the core of Python's data handling capabilities. Welcome to Chapter 11, Societal Impact of Digital Technologies. In this final chapter, we step away from coding and explore how computers and the internet affect our daily lives, society, health, and safety. Understanding responsible digital citizenship is just as important as technical skills. Every time we go online, we leave behind digital footprints, traces of our activity. These include websites we visit, emails we send, purchases we make, and even our IP address and location. Digital footprints are created both intentionally, like a social media post, and unintentionally, like browsing history stored by websites. A critical fact about digital footprints is that they are nearly permanent. Even if you delete a post or photo, the data may still exist on remote servers. This means your online actions can be traced long after you think they are gone. Criminals are often caught precisely because of the digital trails they leave behind. We live in a digital society where most of our daily activities, banking, shopping, education, entertainment, and healthcare, are increasingly driven by digital platforms. Anyone who uses digital technology and the internet is called a digital citizen or a netizen. Being a responsible netizen means using technology safely, ethically, and legally. Net etiquettes are the rules of respectful conduct online. Being ethical means not violating copyright and sharing only verified, true information. Being respectful means honoring others' privacy and diversity. Being responsible means avoiding cyberbullying and not engaging with internet trolls who deliberately provoke people for amusement. Communication etiquettes apply to emails, chats, video calls, and social media posts. Be precise and respect others' time. Avoid unnecessary emails. Keep attachments small or use cloud storage links instead. Be polite in all communications, even in disagreements. And be credible. Your online comments shape your reputation over time. Social media has enormous reach and influence. Practice good social media etiquettes. Use strong passwords and never share them. Be cautious about connecting with strangers whose real intentions you cannot verify. Be skeptical of fake news and misinformation, and think carefully before posting or uploading anything, because what goes online stays online. In the digital age, protecting our personal data is vital. Sensitive data includes biometric information, health records, financial details, and personal documents. If this data is breached, it can cause serious harm. Protection methods include encryption, strong authentication, and access controls. Each country has data protection laws that govern how organizations handle personal information. Intellectual property refers to creations of the mind, inventions, artistic works, designs, names, and logos. These creations are legally protected to give their creators recognition and financial reward. The three main forms of intellectual property protection are copyright, patent, and trademark. Copyright automatically protects original creative works like books, music, photographs, and software code. Patent protects inventions and must be actively applied for, giving the inventor exclusive rights for 20 years. Trademark protects brand identifiers, logos, names, and symbols that distinguish one company's products from another's. There are three key violations of intellectual property rights. Plagiarism means presenting someone else's work or ideas as your own without crediting them. Copyright infringement means using someone's work without their permission, even if you give credit. Trademark infringement means using another company's registered brand without authorization. Open source software makes its code publicly available for anyone to view, modify, and redistribute. The new GPL license is one of the most popular, guaranteeing users the freedom to run, study, and modify software. Creative Commons licenses apply to creative content like music, videos, and text, allowing creators to specify how others may use their work. Software piracy is the unauthorized copying, distribution, or use of commercial software. Even copying software for personal use without a license is illegal. Piracy harms the software industry, discourages innovation, and can expose your computer to malware since pirated software often contains hidden malicious code. Cybercrime includes criminal activities where either the computer is the target or is used as a tool to commit crimes. Common cybercrimes include unauthorized hacking into systems, launching ransomware attacks that hold data hostage, sending phishing emails to steal credentials, and committing banking fraud or identity theft. Hacking is unauthorized access to a computer or network. Ethical hackers, called white hat hackers, are security professionals who look for vulnerabilities and report them to help organizations improve security. Malicious hackers, called black hat hackers, exploit these same vulnerabilities to steal data, extort money, or cause damage. A computer virus is malicious code that copies itself and can corrupt or destroy data. Malware is a broader term for any software designed to cause harm or gain unauthorized access, including viruses, spyware, ransomware, and Trojans. Protecting yourself requires up-to-date antivirus software and careful online behavior. Phishing attacks use fake emails or websites designed to look legitimate, tricking users into entering their username, password, or bank details. Identity theft occurs when someone steals your personal information to impersonate you online. Always verify website URLs and never click suspicious links in emails, even if they appear to come from trusted sources. India's Information Technology Act of 2000 is the primary law governing digital activities in the country. It defines legal frameworks for electronic signatures, digital transactions, and e-governance. Importantly, it also defines and punishes cybercrimes, including hacking, data theft, and online fraud, providing citizens legal protection in the digital space. Excessive use of technology has real consequences for physical and mental health. Prolonged screen time causes digital eye strain, headaches, and disrupted sleep patterns. Poor posture while using computers leads to neck and back pain. Technology addiction, the compulsive, uncontrolled use of devices, is a growing concern, especially among young people. Electronic waste, or e-waste, refers to discarded computers, phones, tablets, and other electronic devices. These contain toxic materials like lead and mercury that can pollute soil and water if not handled properly. We must dispose of e-waste responsibly by taking devices to certified recycling centers rather than throwing them in regular trash. The digital divide refers to the unequal access to digital technologies across different populations. People in rural areas, lower-income households, older generations, and those with less education often have far less access to computers and internet than others. Bridging this divide is a major social challenge, as digital access increasingly determines access to education, jobs, and services. Digital technology has brought enormous benefits to society. We can communicate instantly with anyone in the world through email, messaging, and video calls. E-commerce has transformed business and consumer behavior. Online education platforms put world-class learning resources in the hands of anyone with an internet connection, regardless of geography. Staying safe online requires active effort. Use a strong, unique password for every account and enable two-factor authentication wherever possible. Never share personal details like your address, phone number, or ID documents with strangers online. Regularly check and update your privacy settings on social media to control who can see your information. Responsible technology use means more than just protecting yourself. Before sharing information online, verify that it is accurate. Misinformation spreads faster than truth and can cause real harm. Always respect copyright when using images, music, or text you find online. And practice digital wellness. Take regular breaks from screens to protect your health and maintain a balanced life. Chapter 11 closes our CBSE Class 11 computer science journey. We learned that digital footprints are permanent, that intellectual property must be respected, that cybercrime is real and legally punishable, and that technology brings both great opportunities and serious responsibilities. Being a thoughtful, ethical digital citizen is not optional. It is essential in today's connected world.